So, here's yet another deep learning framework talk, right? So, the obvious question that you might want to ask yourself, well, why do you want to listen to yet another deep learning networks tool talk, right? I mean, haven't we already seen enough in this cafe, there's Torch, Ciano, TensorFlow, CNTK, Keras, Paddle, Chainer, Stinger, Deep Learning for J, and then there are probably about 20 other toolkits who are now didn't mention and were also perfectly reasonable toolkits. So, and you know, you have to ask yourself that when you start building something like this. So, when we started with this, one of the reasons was really the frugality and resource efficiency. So this project, this MXNet, started actually as a university research project. And universities are kind of poor, they don't have all those fancy big GPUs, so we wanted something that ran on old, small, skimpy GPUs, slow network cards, and so on. And we wanted something that basically worked as well as what you would get in industry, but that was cheap. So, the other thing that we wanted is linear scaling. More machines, more data, linearly increased throughput. Likewise, linear scaling in the number of GPUs. We also wanted to have something that was basically as efficient on a single GPU as what you would get otherwise if you were to write optimized C++ code. And last but not least, we wanted to make sure that we don't get into the way of the statistical modeling. In other words, you want to have declarative and imperative code nicely mixed, hence the name MXNet. And to top it all off, please cover all the languages that people usually use, because I don't want to force people to adopt a new language, at the same time actually get good backends that run fast. So this all sounds like a big mouthful. Let me give you a bit of an idea of what it actually means in practice. So an imperative program is usually how everybody learns how to program, which is like, here's a variable, do something to it, here's another variable, do something to it, then add those two variables up, and then print that thing out. That's code on the left. It's very straightforward. A lot of optimization code actually behaves like that. So if you, for instance, want to write an efficient optimizer like Atom or whatever, this is what you do. Compute gradient, add things up, maybe then do some trimming, clipping, whatever, and go ahead. But it's actually a pain to optimize in general. On the other hand, you can do some stuff like this. Declare a variable, then say, well, now C equals B times A, D equals C plus 1, and then you say, now compile the function that I got by actually writing out D, and then execute it. So this is awfully painful as an engineer if you have to write code, but your compiler loves you. That's less flexible. One of the nice things, for instance, there is you can immediately see that, well, basically I can share memory between C and D because, well, as soon as I compute D, C is no longer used, so I can just get rid of it. And this is not just idle computer sciencey thought, but this is actually something that occurs a lot in practice. So, for instance, if you have a very nice, computational graph in your architecture, then declarative programming is really nice. So these are, for instance, the proto files in Caffe. You go and actually declare your network architecture, except that maybe proto files can get long. On the other hand, if you then want to perform certain operations with all the gradients, you basically want to affect the control flow. This is exactly where imperative programming is very nice. And so, well, we went for both. Okay, so to give you a bit of a case in point of what happens, everybody's seen LeNet. If you have not seen LeNet, you should urgently read Jan LeCun's paper from 1995. So this was one of the first reasonable convolutional neural networks applications where handwritten characters were taken. You would basically run them through several convolutional filters, downsample, convolutional filters, downsample with the appropriate nonlinearities in between. And in the end, we had one big fat multi-layer perceptron. Now, in 1995, this was a major effort. Now you can write this in R if you should so desire. And the code below is all the code you need to run MXNet in R. Okay, so now you can do statistics and use deep learning as well. Now, of course, fortunately, things have progressed since then because people have written increasingly big networks. So, for instance, this is one of the versions of the Google Net, and it's big enough that you basically need to tilt your head to actually appreciate the full beauty of it, and each of those blocks has some subunits in it sometimes as well. So basically, this is big. But what you can do is, if you squint at it hard enough, is you can see various repeated structures. Now, only a bad programmer would write a for loop out as one operation after the other. So if I have for I equals 1 to 10, I don't write out print 1, print 2, print 3, but I actually pick the modules and then essentially compose the network based on subnetworks, which is something you can do. Now an example in Python. So this is the same network now in Python in MXNet. Okay. So this way you don't have 1,000 lines of cafe, but maybe 2 screens. I cheated a little bit because you actually need to define what those subnetworks are. So if you look at it carefully, you'll see there's an inception factory and a convolution factory, and that takes another screen of code. But it's fairly convenient. Now, of course, sometimes people really like Caffe, because they've written a lot of code, and it's a good tool, they're used to it. Well, fine, let's call Caffe operators in MXNet. You can do that. And so, while this is a little bit more awkward than writing Caffe code, if you have specific pieces of code that have to be written in Caffe, you can do that. And this is basically just defining one fully connected layer, a nonlinearity and a tangent, another fully connected layer, and then a softmax. That would be Caffe. Now, something else is torch, and as a matter of fact, the next talk after this is about torch. If you want to do torch in MXNet, yes, you can do it. You can take basically modules from torch and you can execute them in MXNet. Inline. This is all nicely done in Python code. So this is nice, and this would be quite a nice thing to have on a single GPU, but the world has moved on, right? By now we have distributed training, and that's in a way where a lot of the excitement is happening. So now, what actually happens is, we basically took the idea of a parameter server. The idea of that actually dates back 20, 30 years, so it comes actually from AI, from blackboards, and then we use it for topic map on samplers, and disbelief did it, and there's lots of parameter servers out there, but it's basically a bipartite graph. You have workers, you have servers, and they talk to each other. However, if you have GPUs inside a machine, it's an awkward thing to have them talk to each other across the network, even if they sit within the same machine. So what you get is actually multiple layers of a synchronization graph. So basically, what you're starting to do is really high-performance computing meets communication, meets optimization. Okay? Now, I would say it's probably very rare to find somebody who is a very good machine learner who also really understands systems. There are very few of those. And so the people who understand those graphs are not the people who will prove convergence guarantees for algorithms, which is why we decided to make it easy. So if you have multiple GPUs, you add 2 extra lines, number of GPUs, and then you define the GPU context, and this way you can happily optimize over GPUs within a machine. If you have multiple machines, well, you need to introduce them to each other and then set up another synchronization layer. So just like the GPUs talk to each other across the PCI Express bus or across the memory, and that really depends on how many you have in your machine and how they're set up. In the same way, the workers will talk to each other through the parameter servers. Okay. Now, of course, that's all very nice, but does it actually work? So here's a fun picture. This is for up to 256 GPUs, Inception v3, and we have rather nice scaling. So, of course, Inception is just one network. You can try it out for other networks. So you can try out ResNet, you can try out MXNet. And so, all those graphs look perfect, but they're not quite perfect. So what we did is so what you see on the left-hand side is basically the aggregate throughput. That is, number of images processed per second as I increase the number of GPUs. Okay, that's fine. But what I really care about is what's the average throughput per GPU. Right? So it's basically on the right-hand side, you see the same graph as on the left, but now divided by the number of GPUs. So this is basically the performance that you're getting out of a single GPU as you increase the number of GPUs. And the nice thing is that this is a very boring graph. I mean, at least for Inception and ResNet, the line is essentially flat. And yeah, okay, it's not perfect scaling. Perfect scaling would be 128, and we only get 108, but that's sort of kind of good enough. But somehow something seems to have gone wrong with MXNet, right? Well, MXNet is not doing so well. But actually, if you think about it, MXNet has a fairly largish parameter space. And just hitting the GPU to GPU sync, so this is actually where we have two GPU chips on one PCI Express bus card, this is actually where the performance is comes. Okay. So if you want to know how to actually make this happen rather nicely, come to the tutorial tomorrow and you'll see a lot more details. Now, the one thing you might have wondered is, well, okay, processing lots of images is fine, but does it actually learn? And you'll see tomorrow that it actually does learn just as well as if you had a few machines. Now, of course, I realize that MXNet is not the tool that everybody uses, right? And at Amazon, we very much try to meet our customers where they are. And so therefore, we figured, well, let's just make it really easy for data scientists and developers to use whatever tools they want. Okay. So what we've done is we've gone out and compiled MXNet, TensorFlow, Caffe, Torch, Diana, Keras, and we've compiled them and linked them against the right libraries. So NVIDIA drivers if you're running on GPUs, Intel MKL drivers if you're running on Intel machines. Because you don't always want to spend a lot of money on an expensive GPU instance if a very cheap and simple CPU instance is good enough to just try stuff out. And because our AMIs have wonderfully memorable names, we just created a bit.ly, so if you go to bit.ly/deepami, you'll always get the latest AMI. Okay. If you log in, then you'll see wonderful things like this, and here there's the necessary NVIDIA Cloud EULA, which basically means since you're licensing drivers from NVIDIA, you promise to be well behaved. Okay. So this is great if you want to train on 1, 2, up to 16 GPUs. But what if you want to train on maybe 16 computers with 16 GPUs, or even more, right? So then you need to request all the machines, set up the network, configure everything, pre-install everything, or you just use our transformation template. So what this does is it basically automatically goes and requests all the machines for you on your behalf. This is basically infrastructure as code. It sets up the right virtual private cloud, so this way you ensure that nobody else can get in. You have a head node, you have all the workers, all the IP numbers are configured and set up, and so this way the head node knows where all the workers are. All the security roles are set up. If any of those things like NAT gateway or IAM row or so on don't mean anything to you, well, the good news is we've taken care of it for you and you don't have to worry. That's the key point. So it takes 5 minutes and then you're up and running. Now, this is something that will let you run distributed TensorFlow, distributed MXNet, and other things quite nicely, and there are examples on how to do this. So this way you can get distributed whatever network's running in 5 minutes from the get-go. Of course, we don't stop there. So one fun bit, so the NNVM migration is complete as of version 0.91. So this is the neural networks virtual machine, which is basically a abstract backend, such that if you want to support a new piece of processor or other hardware in the backend, you can do that. So the anti-chain for executed TensorFlow code on Torch at some point, just to prove that, yeah, you can do such a thing. We are in the process of becoming an Apache project. We've submitted the proposal. There are a whole bunch of usability improvements that we're working on, installation documentation, native documents, and so on, tutorials, examples, so expect it to be a lot more usable. Platform support for mobile, that's also on our roadmap, obviously, with language bindings to extend those. And yeah, our LSTM performance should get a lot better in the future. Just like everybody else, we are hiring, right? And I've used up my time, so I'll just leave that slide up until somebody unplugs the laptop. Okay, thank you.